In the video about the magnetic force on a moving charged particle in the presence of magnetic field, we saw that the magnetic force experienced by such an electric charge will be equal to the amount of charge q times the cross product between the vector for its velocity v and the vector for the magnetic field b. We also saw that the direction of that magnetic force will be into the plane of the screen here. The question now is, what if that charge is actually confined within the limits of a wire? And it's natural to assume that there will be other charges bound within that wire as well, that they will be also moving more or less with similar velocity. They too will experience magnetic force into the plane. So the longer the wire, the more charges will be flowing through that segment at any given time, and so we'll expect stronger magnetic force to act on that wire. The question is, how much is that force and how it relates to the actual flow of those electric charges. Let's consider the length of that segment. We'll consider a small length, dl, here to ensure that we're working with straight segments, and we'll write the length of that segment as v dt. In a sense, that is the distance that all those charges can actually clear over time dt. So I can replace the vector v with dl over dt. Next, it's always more practical to look at the flow of the total charge through that wire. In other words, we're going to work with the electric current. Remember, the electric current was defined as the amount of electric charge flowing per unit time, measured in amps. The conventional current here will be to the right in the same direction in which the positive charges are flowing. With that, we can write that the total amount of charge flowing through this segment of the wire will be equal to the current I times dt. Now let's go and look at the magnetic force formula. I will mark here the force as dF to indicate that this is the force only on this segment of the wire. If I have longer wire that bends, I have to break it into several segments. Each of them has to be a straight segment, and I have to figure out the magnetic force on each of those segments and then use vector rules to add the forces. So for this segment, we'll have dF will be equal to the total amount of charge flowing through this segment of the wire dq times the cross product between V and B. Now the total amount of charge was related to the electric current, so I will write it as I dt, and the velocity itself, that vector could be written as dl over dt. Here I can see that dt cancels out, and I end up with the formula for the magnetic force on a wire carrying an electric current. dF is equal to I dl cross B. Here I is the amount of current flowing through the wire. dl is the length of this particular segment of the wire. It is essential that we work with small segments so they're always straight. And B is the magnetic field.